All right, in section 5.1, we're going to look at polynomial functions and their graphs. So when we talk about general polynomials, we're talking about equations or functions for that matter that normally have a power higher than 2. I mean, really everything we've been doing so far is considered a polynomial, but we're going to be doing more than linear and more than quadratic. So quadratic equations have a second power. Linear have a first power. We're going to be looking at equations where the highest power could be a 3, 4, or a 5. So this is an example of a polynomial function. And there's some terminology here we need to understand. One is the degree. And the degree is 5 for this particular polynomial because the highest power of any one term is 5. So when we talk about a term, we talk about, I guess, monomials or just items that are separated by plus or minus signs. So we have expressions, 3x to the 5th and then 6x to the 4th and so on. These are all individual terms, okay? So the highest powered term is the one with the 5, so that's my degree. The leading term is 3x to the 5th because it leads the pack, all right? It's the highest term with the highest power. The leading coefficient is the 3. And the other coefficients are 6, -4, 1, 7, and -6. We can also call this term right here the constant term since it does not have an x. So when we talk about polynomials, as I've said, we've been doing polynomials all along. We just have different names for ones we use most often. So if I have an example of a function where we just have one number, p of x equals 3, the degree is 0. Right here is a linear function. Q of x is 4x minus 7, the degree is 1 because we have x to the first power. A quadratic function, x squared plus x, the degree is 2. And now we start moving up into other polynomials. This would be considered a cubic function because we have 2x to the cubed is the highest power, and therefore the degree is 3. Now, this last function, it is a polynomial function, but it is in factored form. So see, I've got 3 factors here. The reason why this is degree 3 is because this is an x to the first, that's an x to the first, and that's an x to the first. So therefore, the way we determine that is we look at the powers. They're all ones of each factor. We add them up, and we get our degree is 3. Because if I multiplied this out, excuse me, I would have x to the third power. Okay, so we'll look at some of those, but you got to understand, the term degree and what it means. All right, so before, we start looking at some of the terminology for a polynomial function, I just want to kind of show you what one might look like. So I'm going to draw just a quick graph. That way I can show you, what we're talking about here, okay? So they look something like this. They're going to have multiple turning points. Okay, we've looked at some of these when we looked at graphs earlier. So it could have 2 turning points like this one. It could have 3 turning points. There's all kinds of different ways these can look. This is one where we have 1, 2, 3 x-intercepts. So we've got lots of different types of polynomial functions, but we're going to be looking at specific items that we need to be able to identify, just like we do with any graph. So, one of the items we want to look at are what we call the real zeros of a polynomial function. So in other words, our zeros are the x-intercepts. So for this polynomial right here, my zeros would be -3, 1, and +3. Those are the zeros. Those are my x-intercepts. So if r is a 0, then what we know is x minus r is a factor. So again, if I have these zeros, my factors are, and it's the opposite sign because x minus -3 becomes x plus 3, x minus 1, x minus 3. Okay, so, your factors are the opposite of the zeros. And we also know that these numbers here are solutions. The reason why they're solutions are because by using the term 0 or x-intercept, what we know is that this equation would actually be set equal to 0. And that's where the term zeros come from, because these values give us a 0, just like when we solved quadratic equations. So that's why they're called zeros. Always keep in mind that the 0 itself is the opposite sign of the factor. Okay? We've got lots of other items we're going to talk about with these polynomials. One of them are turning points. You can see here we have 2 turning points. We have the graph crossing the x-axis here, crosses the x-axis here, and it crosses the x-axis there. Now we're going to look at where we talk about where things just touch the x-axis here shortly, and I will hopefully be able to draw you a picture of that. But there's lots of, things we have to know. We do again have intervals where it's above the x-axis, intervals where it's below the x-axis. So these are all things that we will be identifying. All right. So if I am given a polynomial function and I want to find the zeros, well, if it's in factored form, my zeros are +2, -3, and +1. The degree for this polynomial is 3, because that's a first power, that's a first power, that's a first power. 1 + 1 + 1 is 3, because this is x to the first times x is x cubed. So that's why my degree is 3. Conversely, if we are given the zeros and I want to find the polynomial, well, remember, if r is a 0, x minus r is a factor. So my polynomial would be x plus 3 times x minus 2 times x minus 5. Opposite signs. Now, what we have to do now is we've got to expand this. So the way I expand a polynomial is I'm going to use my FOIL method for these first 2 factors here. Keep in mind that whatever I get here, I multiply by this when I'm done. So I take x times x to get x squared, -2 times x, plus 3 times x, minus 6 times the x minus the 5. Don't forget, combine like terms before you go ahead and continue multiplying. So I get x squared plus 1x minus 6 times x minus 5. Now, I do realize sometimes these get complicated, but it's okay. Because what you do next, it's all about organizing your work, following these steps. You take the x squared times both of these, you take the x times both of these, and then you take the negative 6 times both of these. So I'm just going to give myself a little more room here. X squared times x is x cubed. Don't forget about that exponent. X squared times negative 5 is negative 5x squared. Then I now take the x times the x here to get plus x squared. Take the x times the negative 5 to get negative 5x. And then lastly, I take the negative 6 times the x to get negative 6x. And the negative 6 times the negative 5 to get a positive 30. So I combine my like terms. Negative 5 and positive 1 is negative 4x squared. Negative 5 plus negative 6 is negative 11x. And then I have my plus 30. So, we've expanded the polynomial. We know, we've been told our degree is 3, and that is why. Even though we had this in factored form, see, we could still know that the degree is 3 because that is the first term or the highest powered term when we expand this. But we don't need to expand it to know that the degree is 3. All right, so that's a couple things you'll need to be able to do. You'll be able to need to give the zeros if given a polynomial function, and you'll be needing to create the polynomial function given the zeros. All right. The next topic are zeros and their what we call multiplicities. The multiplicities are pretty much what the exponent is, whether it's an even or an odd exponent. Most of the time, it's going to be a 1. But once in a while, it could be a 2 or it could be a 3 or whatever. So if we have a polynomial in factored form, and if this factor raised to this power is one of the factors of a polynomial, then the zero itself, which is r, is a zero of multiplicity m. So let's look at this polynomial right here, and we want to identify the zeros and the multiplicity for each zero. Now, 5 is not a 0. The reason why 5 is not a 0 is because it does not have an x. Okay? So, therefore, we move to the next factor. We have x minus 2 to the first power. And so, 2 is a 0 of multiplicity 1. And you're going to see what we're talking about with this even and odd multiplicity after we go through this. My next 0 comes from this factor, and it is a negative 3. Remember, the zeros are the opposite signs. So this is a 0, of multiplicity 2. Last factor is the 1 right there. So 1 is a 0 of multiplicity 4. So again, you identify the 0 and its multiplicity, And what that's going to tell us is it's going to tell us where the graph either touches or crosses the x-axis. And that's going to help us construct this graph. So we know at this x-intercept, it's going to cross the x-axis. And at both of these, since these are even, if the r is a zero of even multiplicity, then the graph touches the x-axis. We've already seen an example of what it means to cross the x-axis. And I'm just going to quickly show you what a means to touch the x-axis. So this right here, these touch because they do not cross over. Now this is not this polynomial graph. I'm just showing you that it does not cross over. It touches and goes the other direction. So that's what it means to touch the x-axis. We can also get some other information based on what we know here. One thing I know for this particular polynomial here, I'm still looking at this one, is my degree is 1 plus 2 plus 4, which is 7. That would be my degree. So you add the exponents to get your degree. We need to know this number here for the next two items we're going to talk about. For one thing is the turning points. Now, this does not mean this is how many times it's going to turn. This just tells me the maximum number of turning points is n minus 1, where n is the degree. So for this one, my turning points is 7 minus 1, which is 6. That's your turning points. That's not your degree. Remember, your degree is the 7. The next item is what we call end behavior. And this just kind of means when, it's hard for sometimes to see this, but because we always look at our graphs on a very small scale, very limited number of x values and y values. But when you talk about when x gets really, really big, like 100, 100,000, million, whatever we're talking about, the graph of the polynomial just resembles the graph of the power function y is ax to the n. Now, you don't need to visualize that. You just need to know how to write it. So the letter a is your leading coefficient, and n is the degree. Well, we've already found the degree for this polynomial up here. Since we do have a number out in front other than a 1, this would be my a value. And if we expanded this polynomial, our leading term would be 5x to the 7th power, because that's our degree, that's our leading coefficient. So your end behavior is pretty much your leading term, and this is where we get this. So in this case, a is 5, n is 7. So my end behavior is y is 5x to the 7th. If there's not a number out in front, then it's just regular old x to whatever the degree is. Okay? All right, so those are the items you need to be able to identify. And this takes us to how we're going to graph these. So we're going to find the zeros and the multiplicity of each zero, and that's going to allow us to determine if the graph crosses or touches the x-axis at each zero. We use the zeros to create intervals along the x-axis, so that means we plot them. Then we look at our table of values, and we're going to include points from each interval in the table of values. So these points will determine where the graph is above and below the x-axis. Then we answer the other items, the end behavior, the maximum number of turning points. Then we're going to sketch a smooth curve. Okay? So this is what you got to learn. These are your steps you got to know. Do this, 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 so on. Okay? All right, so let's look at an example here. So when we say analyze the graph, that means we're doing those 6 steps there. So step 1, my zeros. So I've got -2, multiplicity of 1. My next zero is +1. And I'm not going to keep writing this out. Multiplicity of 1. My last zero is a 3 with a multiplicity of 1. So what I know at each zero, it crosses the x-axis. First thing, okay? Now, the second item is we now want to plot these zeros, okay? We want to use our zeros to create what we call intervals. So I'm going to plot at -2, I plot +1, and I plot +3. So basically what I need to know is, see, because I know it crosses here. I know it crosses here. I mean, it's going to go on either side. I know it crosses here. I'm kind of looking at, does it go down, back up, back down again? Or does it come from here, back down, back up again? So what I'm trying to figure out is what's going on to the left of -2. I want to know what's going on between my 2 intercepts here. And I want to know what's going on between these 2 and to the right of the last one. So this is how I create my table of values. So that would be step 3. So step 2, we plotted the zeros. Step 3 is my table of values. So it's a big old table. So I'm going to go through and again kind of choose the -3. I know this right here, so I'm going to include that at -2 because I know that's a 0. I'm going to pick the next number going down my table, which is my 0. Right here is another x-intercept or a 0 at 1, and I know that y value is a 0. Then I go for the number between 1 and 3, which is 2. And then my last value that I'm concerned about is this 4. So I've got 1, 2, 3, 4 intervals created by 3 intercepts, right? 1 interval here, 2nd interval here, 3rd interval here, 4th interval there. Now what I got to do is I've got to find what the y value is when x is -3. So I'm going to find p of -3. And this is -3 plus 2. I'm just substituting up into here, just like we do for any equation we want to graph. And that gives me -1 times -4 times -6, which is -24. And what I know about this point is it is below the x-axis. Okay? I'm not going to create a y scale yet, simply because you'll see some of these numbers can get very small or very large. So we're just going to know that whatever x is -3, it is somewhere below the x-axis because y is negative. I already know I have that point. Next, I'm going to find when x is 0. So that's 0 plus 2, 0 minus 1, and 0 minus 3. You know, and if you keep messing these up, use your calculator. So this is 2 times -1 times -3, which is 6. And that point there is above the x-axis. And it should, because remember, think about, I mean, we're not drawing it yet, but think about what we talked about. It crosses here. At -3, it's -24. It goes up, and then y is 6, and it should come back down, because in between each interval, you've got a turning point or a hump. All right, next thing. We know at 1 is 0, so now we got to find out when x is 2, and it should be below the x-axis based upon the fact that it's crossing here. So when x is 2, y should be negative. So I've got 2 plus 2 times 2 minus 1 times 2 minus 3. And I'm just going to go ahead and start speeding up here. This is 4 times 1 times -1, which is -4. And this is below my x-axis like I thought. And then lastly, when x is 4, again, knowing that it crosses here, it should be above the x-axis. So y should be positive here. And if I do 4 plus 2 times 4 minus 1 times 4 minus 3, I get 18. And 18 is above the x-axis. Okay, so we've got these points here. Before we plot them, the fourth thing we want to do is we want to look at the end behavior. Okay, well, my end behavior, my degree is 3. Don't forget, the way we find our degree is we add up the multiplicities. 1 plus 1 plus 1 is 3. My A is 1 because I have a leading coefficient of 1 here. So my end behavior is y equals x cubed. Don't make it harder than it is. Turning points, maximum number of turning points. 3 minus 1 is 2. Okay, so now we've got the information we need. So let's go ahead and sketch a smooth curve. So I know -3, -24 means it's somewhere down in here. I'm not going to create a scale. I'm just going to know that, you know, I've got a y-intercept above somewhere up in here. When x is 2, you know, I got probably it's a little smaller than the y. And then when x is 4, it's somewhere up here. So I just kind of sketch a smooth curve, just trying to keep things symmetrical. And there you go. So that would be your graph of the polynomial. This video has taken a considerable amount of time, so I realize that. So I'm going to hold off, you know, show you the other example in class, just because I don't want to sit there and make you watch a video for 45 minutes, okay? The only difference in the next polynomial, or the main difference, is we do have a second power, and we can look at what happens when a graph touches the x-axis, okay? So that's the one we'll do. We'll pick up with that in class, but at least now you have an example you can go by to see how we do each step as we move along and how to identify all the terminology. See you in class.